Good afternoon and welcome to ECE 164, Lecture 2. Today we're going to talk about device physics of MOSFETs, specifically focusing on what are called long channel devices. All right, before we get too much into this, I'd like to spend a few minutes talking about the naming convention that we'll try to use and be consistent with throughout this class. This does follow what is called the IEEE style guide. Anytime that we're talking about DC values, we're going to use uppercase symbols with uppercase subscripts. So some examples might be if we were talking about the gate to source voltage, that would be capital V, capital G, capital S, and subscripts like that, or the drain current through device, ID. If we're talking about signal components, we will use lowercase symbols with lowercase subscripts, i.e. VGS or ID. So these are the small signal components of the device. If we're talking about the total instantaneous values, that is the DC plus the small signal component, we will use lowercase symbols with uppercase subscripts, i.e. VGS and ID. And then lastly, supply voltages really are just a subset of this initial example that we gave up here. That is that they're going to be uppercase symbols and uppercase subscripts. Okay. And then shown down here in the bottom is simply this example where I'm trying to show the instantaneous value of a signal where this is VGS is equal to the DC bias that's on the signal plus the AC or the signal component of that. Okay. The notes, I will be very, very consistent in using this type of methodology. I have bad enough penmanship that it's hard enough to read, yet alone differentiate between a capital and a lowercase v. I will be a little bit sloppier when I'm writing, and I'll just try to be as neat as possible, but I won't follow this naming convention there. All right, so let's start with the basic fundamental operation of what's called a MOSFET. What we're showing here is that we have this cross-section of a device, like we talked about in the last lecture. We have a P-type substrate. We have an N-plus diffusion, N-plus diffusion. These are forming the source and the drain of this device. We have a gate that's in between these, and this diffusion are separated by length L. This is the length of the device. How far they project into the screen, that's the width of the device. Next, we'll look at what happens when we start to apply some voltages to this device, and we're going to start with the simplest one, and that is where we're applying 0 volts to all of the terminals. Okay, so namely the source, the drain, the gate, and the body or the bulk. They mean the same thing. If they all have 0 volts, then this device is essentially off. Okay, and when I say off, it means that we're not conducting current between the drain and the source, and we really have no substantial currents flowing anywhere in this device. These diodes are 0 biased in this case, and there's no path between the drain and the source. We essentially have 2 reverse bias diodes in series here if we were to go look at this pathway across here. All right, so we would call this device off. Now, let's look at what happened when I leave the source and the drain biased with 0 volts, okay? But the body is still at 0 volts as well. And now I start to apply a gate to source voltage that is greater than 0. What I'm essentially doing is I am now creating an electric field. And I'm creating an electric field in this vertical direction, okay? And this electric field is pulling all of the electrons closer towards this edge, okay? And when I'm doing this, I'm taking this P-type substrate, which has a lot of donors, but is deficient of electrons. Its majority carriers are holes, okay? And what I'm doing is that if I increase this voltage here large enough, I can invert the material near the surface of this device. And when I say invert, it means that I'm forming an N-type layer, okay, a virtual N-type device. This is what we would call an inversion layer. I'm taking the P-type that has a lot of holes, it's deficient in electrons, the electric field is pulling the electrons closer to the surface of this device. Once I look here, now I have an excess of electrons. This is making this appear like an N-type channel. Okay? And so I've applied enough voltage to invert the surface. Okay? Importantly, now I have an N plus, N, N plus. So I have an ohmic contact between the drain and the source. Okay? And so we'll see what would happen in just a second if I was to start to apply some voltage between the drain and the source. Now the voltage that this happens at is what we're going to call the threshold voltage. That is, when I change this from a p-type to an n-type material, that's what's going to be called the threshold voltage, or VT. Okay? And I'm going to go into a little bit more detail later on, exactly a little more mathematical about how we would derive that voltage. Okay? The important part here is that I have inverted the material, and now I have a conductive channel between the source and the drain. All right, so now I'm going to leave the source at ground, the body still at ground. I have my gate to source voltage that is inverting this material, and now let's start to apply a little bit of drain to source voltage. Okay? What I'm going to get is I'm going to get a current. Okay, I'm going to get a current that's flowing because now I have a vertical electric field that is inverting this channel, and I have a horizontal electric field that is pushing the electrons between the drain and the source. What we want to do is we want to try to calculate this current as a function of these two voltages. That is, as a function of VGS and of VDS. Okay? And so what we're doing here is we're kind of just getting the foundation laid, and we're getting our intuition built up. In just a second, we're going to rigorously mathematically derive what this current is. Okay? Now, in order to do this, we need to make a few assumptions. And I'm going to walk through these assumptions and very explicitly state them up front. We will revisit them in, 20 minutes, and we'll try to understand if they're good or bad assumptions. Okay? The first one is that the current is controlled by the mobile charge in the channel. Simply said, this is describing that if I were to calculate the carrier density within the channel, this will allow me to calculate the current. Okay? It turns out that this is a really good approximation. Okay? The next thing that we're assuming is that the vertical field is what sets this channel charge. And so we can approximate the available mobile charge through the voltage difference between the gate and the channel. This is an okay assumption. It turns out that depending on the region of operation of the device, this may or may not be a very good assumption. We will revisit this very shortly. The third assumption, that the carrier velocity is proportional to the lateral field. Okay? So simply said that the electrons or the carriers that are moving, if I apply a horizontal electric field that is between the drain and the source, the velocity of these carriers will depend on that voltage. It turns out that this is a terrible assumption. We'll show a little bit later why, but essentially there's a speed limit that is imposed on how fast these carriers can go. And if we keep trying to apply higher electric fields, the carriers cannot move any faster. Okay? And so that's why this breaks down, and this is a very bad assumption. The last assumption is that there's no current below the threshold voltage. This is another bad assumption. We're going to talk a little bit later about that in this class. All right, so let's go back to our setup and let's look at our cross-section of our MOSFET. Again here, source, drain, gate, body. We're tying a particular voltage to the gate relative to the body. We're calling this VGS, or rather to the source, not the body. And then we're defining geometrically that this is going to be x equals 0, and across the length of the channel up to the drain, this is going to be as x equals L. All right, so now we know that if we don't have a channel, that IDS, or the current between the drain and the source, is equal to 0. When we have VGS is greater than VT, that is that we have enough voltage to form a channel, we now can calculate exactly how much charge there is at any point along this channel. Okay, and so this is really just Q equals CV. Okay? And so Q of X, or the charge at any point along this channel, is equal to the oxide capacitance, okay, where the oxide capacitance is relative to the permeativity of this material as well as the thickness of this material. The voltage that we're applying, VGS, minus this voltage, the threshold voltage that we have to overcome. Okay? And then if there is any voltage that's being dropped across this channel, that's V of X. Okay? So simply said, the charge at any point along this channel is equal to the oxide capacitance times the delta voltage or delta V that we have anywhere in this. The negative sign I should point out in this equation is that we're talking about electrons which have a negative charge. This oxide capacitance is equal to EOX divided by TOX. EOX is the permittivity of this oxide layer here, which is 3.9 times epsilon naught for silicon dioxide, which is about 34.5 picofarads per meter. The oxide thickness, typically this will be measured in nanometers, anywhere from about 5 to 50 nanometers for a typical MOSFET. Oh, there's one other thing I should point out. Back here, in addition to forming this channel, we are also forming what's called the depletion region. And this depletion region is because we have reverse bias diodes here, and we are pulling all of the electrons closer to the surface while we're repelling or pushing away the holes. Okay, and so this is creating this region here, which is known as the depletion region, where it's essentially devoid of mobile charge. All right, so now that we have the charge at any point along this channel, we need to now calculate how quickly that charge moves. Okay? And so the drift velocity, we're going to write Vd of x, is equal to the mobility, or mu, times the electric field. Okay? And this electric field is equal to the voltage that I'm applying divided by the distance, so dV dx. Okay? Now I should mention that here we're applying a very small VDS. Okay, and the reason for the small VDS is going to become apparent shortly, but just know that this derivation is set up for small VDS. Then the drain current, that is the current that's flowing from the source to the drain, can be written as ISD is equal to the width of the device, that is in the third dimension here that we're not showing, how wide is the device, times the mobile charge at any point along this channel, times how fast those carriers move at that point in the channel, which we can then plug in for Q of x and Vd of x, the drift velocity that we just calculated. We get that the current from the source to the drain is equal to minus W times Cox, VGS minus V of x minus Vt times the mobility times the electric field, dV dx. We're going to do a couple of things. One, we're going to actually want to talk about the current from the drain to the source rather than the source to the drain. So that's going to get rid of this negative sign. And then I'm going to start to integrate this. And so I want to move dx terms to the left side and leave dv terms on the right side. And so we can separate this. It's a very simple integral to integrate. We're going to integrate on the left side from 0 to L, that is the length of this device. On the right side, we're going to integrate from 0 to VDS, that is the boundary conditions of the voltage right at the edge of the source and the boundary condition right at the edge of the drain. All right, so we're solving this differential equation. After a very little amount of math, we can show that the drain to source current is equal to mu n Cox W over L times VGS minus VT times VDS minus 1/2 VDS squared. Okay. Now, before going too much into kind of the rest of this, we should do a little bit of a sanity check. We should just kind of think about all of these parameters and how they would affect the performance of this device. Okay, and so let's do a very simple thought experiment. If this device was wider, i.e. in the third dimension that I'm describing here, if it was more devices in parallel, should that result in higher current? And the answer is yes, right? So more width should give us more current. What about this oxide capacitance terms? What happens if I make the oxide thinner? If I make the oxide thinner, then I have more what's called control over the channel or channel control, and that should give me more current. Okay, and so this kind of intuitively all reasons out. If I was to make the device longer, okay, that is that I separated the drain and the source further, I would end up with less current for the same voltages applied everywhere else. Okay? And so if I apply a larger voltage between the drain and the source, that is to create a higher lateral electric field, I should get a higher current, okay, at least to first order for a small VDS. And then lastly, if I apply a higher VGS, that is to get a higher gate to source voltage, this creates a larger vertical electric field, and again, I would expect more current. Okay, so all of these kind of intuitively match with our understanding of how the MOSFET should work. We did make one assumption here, and that is that this channel has uniform depth. And so if you look kind of back at the previous picture, the way that I've even drawn this is a rectangular shaped channel, okay? This is by virtue of us applying a small VDS, and we're gonna see what happens in just a minute when this is not the case. But essentially what I'm saying is that the small VDS allows me to invert the channel uniformly from x equals 0 to x equals L. All right, so we would call this what's called the linear region of operation. And the linear region of operation occurs when I have VGS is greater than VT. Okay, so that's simply to say that I've created this inversion layer, and I have VDS is less than VGS minus VT. Okay, this term here, we usually call this what's called the overdrive voltage, or VOV. That is how much voltage we're applying beyond what I need to invert the channel. The device in this configuration, it essentially looks like a voltage controlled resistor. Okay, and the easiest way to see that is that the second order term here is going to be relatively small compared to the first order term. And so now we have a linear relationship. Okay, this essentially looks just like Ohm's law, where I could write that the drain to source current was equal to VDS divided by RDS, where RDS, or the resistance between the drain and the source, was defined as this. Okay, and so here, this really gives me a way of taking a transistor, and with these kind of voltage conditions, I can effectively make this device operate like a voltage controlled resistor. Okay, that is to say that I can adjust the resistance by playing with W, playing with L, or the voltage that I'm applying between the gate and the source. If we look at a couple of different plots here shown on the lower right, I'm plotting the drain current versus the drain to source voltage, and I'm showing you a family of curves for different VGS. Okay, and so exactly what you would expect, that as we apply higher VGS, we get a steeper slope, which would mean that we have a lower resistance path between the drain and the source. Importantly, though, all of these are indeed linear, okay? And so that is kind of confirming our analysis that we've done so far, that this device looks like a voltage-controlled resistor, again, provided these conditions. So now we should be asking ourselves, what happens if I start to increase that drain to source voltage? Okay? For small VDS, I could neglect this squared term. What happens as I start to crank it up? Right? And it turns out that if you increase VDS and we were to plot IDS versus VDS just using this equation, we would end up with something that looked like this, okay? Which is not surprising that we have a second order term here, so it gives you an inverted parabola. Intuitively, we should stop and think about this for a second. Um, for this curve, I've applied a fixed VGS minus VT. Okay? And so as I'm increasing the VDS, the current is going up, it's starting to plateau. I'm applying more VDS, but I'm actually getting less current, okay? And so what this would actually look like over here is a negative resistance. Positive resistance, flat, negative resistance, okay? And so this should start to kind of raise some alarm bells that something is not quite right, okay? And it turns out that this is not actually a correct assumption. Something is wrong in our model, okay? And so what's happening is, if you think very carefully about the assumption that we made, when we were applying a small VDS, I said that the channel would be uniformly inverted, okay? And it turns out that this uniform inversion layer is no longer true under these conditions, okay? And so if we think about what this looks like, if I have this device, and here's my source, here's my drain, okay? With small VDS, I can essentially invert the entire channel uniformly. However, if we look at this, recall that when I said that we were able to invert the channel, I had to have the voltage at each point along this channel, that is V of X, be greater than VT. Okay? The important thing here is that if I was to think about the voltage VGD, that is the gate to drain voltage, okay? The gate to drain voltage is equal to VGS, that is the voltage between the gate and the source, minus the voltage drop that I have to go to get back from the source up to the drain, okay? And it turns out that this voltage is less than VT. And so what this means is that I'm not really inverting the channel uniformly, but rather I'm inverting it in a fashion that looks more like this, okay? So I'm inverting it in a triangular pattern, not in a uniform pattern. And right at this edge over here, I'm not actually inverting the channel at all, okay? There's no inversion layer right at the edge of the drain. And so this is fundamentally why our model here is not correct above a certain point. And so we need to go back in and we need to modify our model to take into account this channel that is no longer rectangular, but is now triangular in nature. All right, so as we keep increasing VDS from a small value, the channel is becoming narrower over at this drain, okay? When the gate to source minus the VDS is equal to 0, that means that we've essentially not inverted the channel at that point. And so you might ask, well, how do we have a conductive path between the drain and the source then? It turns out that there's a very, very large electric field, okay? Any voltage that I can't drop, that is excess voltage of VDS that I'm not dropping in the channel, it sweeps the carriers across this very, very short region, okay, this depletion region. And so what this means is that at this point in time, I'm pinning this drain to source voltage at VGS minus VT. Okay? Remember, that's the exact point when I'm pinching it off and I'm no longer able to invert it. So if you think about the geometric constraint of this, it's essentially like this is going to right at this edge of 0 here, that I'm not inverting this last point. Okay? And so if I pin VDS at VGS minus VT, that is, I simply substitute in these values, and I start to simplify this expression, I will get the equation that IDS is equal to 1/2 mu n Cox W over L, VGS minus VT squared. Okay? Importantly, the current is now independent of VDS. Okay? And so if you were to think about other types of devices, circuit elements that this represents, you would no longer say that this is a voltage controlled resistor. You would actually say that this looks more like a voltage controlled current source, okay, where VGS sets the amount of current that I have in this device. All right, so a couple of other things that we simplify out in this device. Mu n Cox, we usually lump these together and call this Kn prime. This is a technology parameter that's known as the transconductance parameter. W over L, these are knobs that we as designers can turn. We can change the width, we can change the length within the constraints of the foundry and the technology. The gate to source voltage, that's up to us on what we apply. The threshold voltage is usually also set by technology. The voltage that we're applying, the difference between VGS and VT, we call that the overdrive voltage. That's VOV. Sometimes in discrete devices, you'll lump mu n Cox and W over L all together and call that Kn. As integrated circuit designers, we usually do not do that because we want to keep W over L in our control and be able to adjust these parameters. All right, so let's look at some IV characteristics. So what we're showing here is VDS along the x-axis, ID along the y-axis, and we've picked one particular family of this curve. So we're applying a fixed VGS or a given VGS or overdrive voltage. At small VDS, this device essentially looks relatively linear. Okay, and so this device is acting like this voltage controlled resistor. The device is in the linear or triode region of operation until we get VDS being larger than VOV. Okay? At this point, we're getting into this point where we're going to call it VDS sat. That's the point when we're transitioning from triode into saturation. And at this point, at least based on our first order model that we've derived, the current is now independent of VDS. That is, it's a flat line. It no longer depends on what voltage we're applying between the drain and the source. Okay? And so these are the two equations that we would use to plot this. This is the equation we would use in triode. This is the equation that we would use in saturation. And of course, they're going to be continuous right at this point where we're overlapping between them. If now we were to look at a family of curves where we're sweeping VGS, we would get something that looks like this. Okay, and so here for one particular overdrive voltage, as we increase the overdrive voltage, we would expect the current to go up by the square of VOV. And so linearly sweeping VOV, each of these should get squared larger from the previous one. So a 2x in VOV should give us a 4x difference in currents here. Okay? Again, we see the triode region, we see saturation region, and we see that the device enters or crosses over between triode and saturation at different points along this curve. Also shown is a curve where we have a VGS that is less than VT. And in that case, we have no current in our simplistic model. The device is essentially in cutoff. So this is what's known as the long channel device model. And what I want to do now is add on a few additional tweaks to this that is going to make this device a little more representative of the transistors that we're going to use in this class. And by the way, one of the very first things that you will do, and you need to do this in our class as well, is characterize the technology. And one of the ways of characterizing the technology is to generate these types of IV curves for the different transistors, i.e. for the NMOS and the PMOS and any other flavors of those devices that you might have. All right, so one of the things that we've assumed so far is that the pinch-off point remains at the drain. Okay, and so that is to say that I have a rectangular or a triangularly shaped channel, and regardless of the lateral electric field, that is the voltage that I'm applying between the drain and the source, this is staying stationary. Okay? It turns out that that's not quite correct. What happens is you get an effect that's known as channel length modulation. And channel length modulation is essentially that I'm moving this pinch off point away from the drain and closer to the source as I apply a higher voltage at the drain. Okay? The idea of channel length modulation essentially comes that I can calculate how far I'm moving this back, this delta L, and so the channel now effectively looks a little bit shorter than it was before. And so the impact of this on our IV curves is that they are no longer perfectly flat here. They no longer look like perfect current sources, that we now have a finite slope to them. Okay, and the slope is inversely proportional to what we'll call the output resistance, which we'll talk a little bit about in the small signal model coming up. Interestingly enough, if you were to take all of this family of curves and you extrapolate them back into where they would intercept the y-axis, this is what's known as the early voltage, or minus VA. We often talk about this in terms of 1 over lambda, where VA is equal to 1 over lambda. Now, if I want to add this, this band-aid, if you will, to my small signal or my IV curve, I essentially take the curve that we've derived previously in saturation, and I add this 1 plus lambda VDS term. And this lambda VDS term is what gives us this finite slope in saturation. Okay. All right, so we also should talk a little bit about what's called the body effect. And if you think back about the way that we've constructed this MOSFET, remember that we have these drain to source, source to body and drain to body diodes that we want to try to keep reverse biased. And the reason for that is very simple. I want the currents to flow from the drain to the source, not the drain into the body. And so I want to minimize this type of current path or this type of current path. Okay? And so typically what that means is that I will tie the body to the highest voltage, to VDD. Okay? You can also tie the body to a different voltage, okay? And that is that if I don't have the source and the body tied to the same voltage, you can essentially change the threshold voltage. You can make this channel either harder or easier to invert. And so what this looks like is a change in the threshold voltage. And so if we don't have the body to source, or VSB is equal to 0, we need to calculate the effective threshold voltage. And the effective threshold voltage is equal to VT naught. This is with 0 bias applied, plus gamma, which is a parameter based on the technology, times square root of 2 phi f plus VSB minus square root of absolute value of 2 phi f. This is the work function of the particular device. And so essentially what this lets us do is this lets us somewhat modulate the threshold voltage by either making it easier to invert, or if we wanted, making it harder to invert by playing with this body voltage. Okay. You should always assume that the source and the body are tied together unless we're explicitly showing you in the schematic that it's not indeed that way. And this does bring up one thing that we should mention, and that's that anytime you're doing integration where you have lots of transistors, unless you have what's called a triple well process, it means that the body for all of the NMOS devices has to be the same. Okay? And so when it has to be the same, I no longer have the option to play around with tying it to the source or tying it to some intermediate voltage, because I have to do it for every one of the NMOS transistors. The PMOS, on the other hand, the PMOS is in what's called a well. It's in a tub that we've doped with N-type silicon. And so there we can have the ability to tie the body essentially to whatever voltage we want. We could tie it to the source, we could tie it to VDD, whereas most often for an NMOS, the body is going to be tied to ground, to VSS. All right, so here we're showing an NMOS device and a PMOS device. Um, as I just said, the NMOS device, all of the transistors are made within this P-type silicon, and if you were to kind of imagine what they look like, I would have many more of them all sharing this same body. Okay, the PMOS is essentially the opposite of what we derived for an NMOS. Okay, so instead of forming a virtual N channel as we did for the NMOS, I'm going to form a virtual P channel for the PMOS. Now, I'm also going to have holes as my carriers instead of electrons. And so if you think about all of the IV equations, they're going to be like the NMOS equations with a few exceptions. One, all of the voltages are going to be negative. Okay? And so the easiest way that we can deal with this is simply flip the order of the terminals. So instead of using VGS, we use VSG. Okay? And this literally is the exact same thing as saying that it was negative given our definition of VSG. So anytime we write something like VSG, this is equal to VS minus VG. Okay? And so it's very easy to see that if I was to say VGS instead, it's simply the negative of this. The other thing that we're going to do is we're going to use the mobility of holes, mu p, instead of the mobility of the electrons, mu n. Okay? And so typically what you'll find is that mu n is 2.5 to 3 times more than mu p, which is to say that it has higher mobility, the electrons can move faster. As you go into more advanced technology nodes, and when I say more advanced, 45 nanometer and below, mu n and mu p, once you start to get into strained silicon, they start to approach each other and they're actually about the same. All right, so to quickly summarize, for an NMOS, if we have VOV is less than 0, we're going to say that the device is in cutoff and that its drain current is equal to 0. If we have VOV greater than 0 and VDS is less than VOV, the device is in triode or the linear region of operation. It looks a lot like a voltage-controlled resistor, and it's governed by this expression, which we derived from first principles. If we have VOV greater than 0 and VDS is greater than VOV, then the device is in saturation, and the current is governed by this expression, where we got this by taking VDS was equal to VGS minus VOV, plugging it in and solving. We've added on the channel length modulation. For a PMOS, the exact same expressions. As I said, we're just going to flip the parameters here. Instead of VDS, we're going to talk about VSD. VGS, I'm going to use VSG, and I'm going to take the absolute value of the threshold voltage because it is going to be negative in order to derive the overdrive voltage. But if you look at these equations after we make those simple changes, they're identical. Okay, and so this is the methodology that I will follow in this class. If you learned a different way, it's perfectly fine. There's lots of ways of approaching this. Okay, so to summarize our first order behavior graphically, if we have any kind of voltage that we're applying VGS that's less than VT, we're in sub-threshold, we're going to get no current. If we are applying VGS that's greater than VT, and we have VDS that is less than VGS minus VT, the device is in triode. It looks a lot like a voltage-controlled resistor. As we keep increasing VDS, the device enters this region called saturation, where it looks a lot more like a voltage-controlled current source rather than a resistor. All right, so here we're looking at a couple of different IV plots. On the left here, we're looking at ID versus VGS. Okay? And so as we start to increase this gate to source voltage, we have no inversion layer up until we get to this threshold voltage, VTN, after which it looks quadratic in how it increases relative to VGS. On the other hand, if we were to plot ID versus VDS, we would see that we have a linear transfer curve until we get towards the edge of triode. And then once we enter saturation, we end up with a current that is no longer dependent on VDS. So what are the limitations of this model? There's a couple of things that we built up when we were doing this. This is a good way to understand the fundamental principles of how a MOSFET works. This is what's known as the long channel, the quadratic, or the low field model. However, there's a lot of things that, that don't really accurately describe modern MOSFETs. And the biggest way to summarize this is to say that as we've done things like shrink the channel length, we've increased the electric fields dramatically. Okay, and so our assumptions of low electric fields no longer hold. Okay, the device physics right around VGS is equal to VT are actually very complicated. Our model assumed only drift in the conduction mechanism, that is how we conduct current between the drain and the source. It turns out that once we're below this voltage, or even right at it, it's actually a complex combination of drift and diffusion, and so our simple model does not capture that. This also says that the drain to source current below VT is not going to abruptly go to zero. In fact, it's going to have sub-threshold current, which we'll talk about a little bit later. However, what we want to understand from this is very simple kind of back of the envelope equations that get us understanding of the general knobs that one has available to design with. Okay. All right, so let's think a little bit about some of the kind of intuitive reasoning that we can get from these models. And so we'll ask ourselves a couple of questions and kind of work through examples. So we're showing here a family of curves, okay? And I should mention that this is for an old technology, okay? And I have to show you old technologies because this is being distributed. And distributed meaning that it's online, that even if it was in class, I can't actually show you the technology that we're using in this class. Those are protected by the NDA, and the NDA even applies to me in the sense that I cannot publicly disclose these numbers. And so these are all from an old textbook. The voltages and everything are going to be much higher than we use, but the general principles are still the same. All right, so what happens if I take this family of curves and I was to change VT naught? So recall back that VT naught was the threshold voltage when I'm applying zero bias between the source and the body. Okay? And so if I take a VT naught of 1 volt and I was to increase that to 1.2 volts, what you would see is that all of these curves would shift down. Okay? And so intuitively, this should make perfect sense because I'm getting less overdrive voltage for this particular gate to source voltage that I'm applying. What were to happen if we were to change the oxide thickness? Okay, so what were to happen if I was to taking the oxide thickness from 100 nanometers and I increased it to 120 nanometers? Remember, if you recall back that the capacitance, Cox, was Eox over Tox. And what this does is this affects the transconductance parameter. And so if I increase Tox, I'm lowering the transconductance parameter, that linear Kn factor, and so I should result in lower current for the same gate to source voltage. Okay. And you'll notice that this is a linear term very much because it's just linearly multiplied. It's not in the square portion of the equation. All right, what would happen if I was to change Kp or Kn? Again, the transconductance parameter, if Kp went from 29 up to 34, this would result in an increase in current because I have higher transconductance for a given gate to source voltage, I'm getting more current out of the device. Now let's look at what was to happen if I was to play with the body to source voltage. So for a fixed width and length device, if I have VBS is equal to 0 volts, in the linear region of operation, I would get a linear IV curve as a respect from VGS to ID. And if I was to increase the threshold voltage, it would simply shift this curve to the right and down. And so what that means is that for that same VGS that I'm applying to this, I'm getting less current because I've essentially increased the threshold voltage. Now, if I was to take this VBS at 0 and I was to decrease it to minus 5 volts, what I'm doing here is I'm making the channel harder to invert. And by making it harder to invert, it means that for that same amount of VGS here, I'm getting less current out of the device where I've applied a negative VBS. So essentially what I'm doing is I'm increasing VT in the same way that in this previous example we went from 1 volt to 1.2 volts. Here I'm shifting it even further than that. And so this gives us a very powerful knob if we wanted to play with it in order to modulate the threshold voltage. And again, if we were to look here at the oxide thickness in linear region, we can see the same effect that we can shift these curves to the right and end up with lower current given that we increased the oxide thickness, which gave us lower channel control. Okay. I should mention that TOX is usually not a parameter that we have control over as designers. It's usually the process that specifies a particular oxide thickness. All right, and then just for completeness, we can look at what happens with KP. KP, we could get there from COX, or we could also get there from a change in mobility. And you can see that, again, here, if I had this curve and I was to now start to play with different amounts of KP on it, I would get more current for a higher KP, which should be very intuitive. I'm getting more transconductance for a fixed gate to source voltage. All right, so this is an appropriate time to start talking about the design space. I liken analog circuit design to what it looks like when you look in the cockpit of a plane. There's a whole bunch of knobs, and it's not always clear which knob you should be turning in order to accomplish your objective. Okay? It is important to understand what parameters we have within our control and what parameters we really can't change. Okay? And so the width of the device, we can always change that. As analog circuit designers, that's one of the primary knobs that we have in our control, that we can change the width in order to increase the transconductance of this particular device or the current that we want out of it. The length, most of the time we can change. In very advanced process nodes, it turns out that they're often highly quantized and we can't really change them. The voltages that we're applying to the device, i.e. the overdrive voltage, we can always change that. That's always something that's in our design space. But there's a lot of things like the technology parameters that we really can't change. The threshold voltage, it's set at the time of manufacturing by how much dopants are implanted in the channel. We do have a little bit of control over this with the body to source voltage. The oxide thickness, we can never change that. The capacitance, we can never change. The mobility, we can never change. And Kn, per all of these above, we really don't have the ability to change that either. So when we're talking about the design space, it's really primarily these parameters. It's the width, the length, and then the voltages that we're applying to the particular device. All right, so let's quickly revisit some of these assumptions. We already took care of number 2. Okay, so number 2, we just had to account for the channel geometry in order to correctly assess that. But I want to revisit kind of 3 and 4 and spend just a few minutes talking about why they're so bad assumptions, and what we can do to maybe fix them in our equations. All right, so what I'm plotting here is the charge in the channel um, as a function of the overdrive voltage. Okay, and what we see is that there's really a few components that make up this charge. This black line is the total charge, which is composed of the mobile charge, which is what we are actually bringing up to the surface, and there's some fixed charge that's always going to be at that particular position. Um, and what we see is that at VT is equal to VOV, that is right here, or around VT rather, where VOV is equal to 0 volts, this is where this channel charge, the total charge, starts to become very linear, and it starts to follow the mobile charge in the channel. This is exactly what we assumed within our model. However, if you look what's going on right at VT and below, it's a much more complicated expression, and we should realize that there is, even though we're not having any mobile charge with VOV is less than 0, there is still some fixed charge and therefore some total charge that is in the channel. And so this is going to give rise to that current that we were talking about. And we'll revisit this in just a few slides, but this sets up the idea that we have charge within the channel. All right, so now let's talk about that other assumption that we made with regard to how fast the electrons could move, or the carriers. It turns out that once the electric field gets to be very high, the carrier velocity is no longer proportional to the electric field. Okay, and the analogy that I always like to give with this is, let's say that you have a sports car. Okay, and your sports car is it's a Shelby GT500 Mustang. Okay, one of my favorite cars, capable of driving 200 miles an hour. If you're on the I-5 at 5 p.m., it doesn't matter how fast your car is. All of the other cars around you prohibit you from going any faster. The same thing happens inside of the channel. All of the other carriers and all of those fixed charge that are stuck within the channel that we put in there to set the VT, we start bumping into them, and we can't ever go any faster without bumping into people. Okay? And so this is what's known as velocity saturation. And the carrier is saturated about 10 to the 7th centimeters per second, irregardless of the carrier mechanism, so for both electrons and for holes. And so if we were to look at the current, ID versus VDS, our long channel model would predict that we have something like this, okay, where after we get VGS minus VT, we enter saturation. However, the short channel device says that once I get to the saturation voltage, that is, once I get to the maximum velocity that these carriers can move, that is VD sat, I have a linear rather than a quadratic relationship between the voltage and the current. Okay? And so what happens here is that the velocity is no longer proportional to the electric field. Okay? I can only go so fast, despite having a GT500. Okay, so what are some of the outcomes of this? Well, one, we're going to get less current than we would predict by our square law model. Two, instead of the current increasing quadratically with an increase in VOV, it's now going to increase linearly. And so if we look down here at some IV curves that are plotted from a short channel device, you can see that from 1 volt to 1.5 to 2 to 2.5, I'm not getting that quadratic increase in the current. Okay? And so what this means is that we model this by saying that the carrier velocity is proportional to the electric field as long as the electric field is less than the critical value. And so for any value less than EC, we use this expression. Once we have an electric field that's greater than the critical value, than the critical electric field, it becomes pinned. It stops. Okay? And so one way of accounting for this in our model is to add this preterm in front. Okay, and so this preterm in front essentially accounts for the velocity saturation model, or accounts for the mobility loss that we have at higher VDS. And so you can imagine that it's a function of L for longer channels. It's not as important as for short channels where I have very high electric fields given the short distance that VDS has to drop. And so for very short channel devices, what that means is that this prefactor here is going to be less than 1. And for long channel devices, that is large L, this is going to approach 1 or be equal to 1. There's a few other short channel effects which we won't spend a whole lot of time talking about in this class. I will just briefly mention them so that we're aware of them. We talked about velocity saturation. We didn't really talk about drain-induced barrier lowering, or what's called DIBBLE. DIBBLE essentially says that any voltage that I'm applying on the drain can influence the mobile charge in the channel in the same way that the back gate modulates it. And so VT can also be a function of the voltage that I'm applying on the drain. You know, I can essentially lower it. That's what's known as drain-induced barrier lowering. I can get an effect known as hot carriers. Given that I'm applying a very large electric field between the gate and the source of a MOSFET, I can get carriers that become trapped in the oxide. Okay, so I have very, very large electric fields across this small oxide. Some of those carriers can become impregnated into the oxide, and what this does is now, the next time that I apply that same voltage, I have charge that's stored in the oxide. This is going to shift around the threshold voltage. Okay. More importantly, over long periods of time, it causes degradation in the performance or reliability concerns for this device. And so shown here are some stress measurements that people have taken for ID versus VDS curves. If you measure ID versus VDS of a fresh new device, it looks something like this. As the device becomes degraded from carriers being trapped in the oxide, it starts to shift over here. It looks like we're applying less overdrive voltage than we really are. Okay, and it should be mentioned that, you know, this doesn't have to be a long-term thing. In some cases, due to the very high electric fields, this can be as short as, you know, an hour or a couple of hours. All right, let's revisit very quickly this idea of sub-threshold conduction and what happens when we have an overdrive voltage that's less than 0 volts. When I showed you this plot earlier of mobile charge in the channel versus overdrive voltage, I had a linear y-axis for the mobile charge. Okay, and if we were to plot this on a log axis, what we see is that actually there still is some charge that is mobile in this channel, even when I have no overdrive voltage. Okay, once I get above this, it becomes linear, but there still is charge that's present down here. Okay, and this is just, you know, fundamental to solid state physics. This is not relative just to short channel device. Any MOSFET is going to have this sub-threshold conduction. And so what does this mean? Well, it really means that the device looks a lot like a bipolar junction transistor. You know, if I think about having an N+, PMOS or a P-type here, I really have an NPN or a BJT transistor. Okay? The interesting part about it is that the way that I control this base voltage is through a capacitive divider. Okay, and the capacitive divider happens to be from the oxide capacitance that I have here and the depletion capacitance that I have between the substrate and the channel here. And so this ratio of these two capacitances, that is CJS plus COX divided by COX, is approximately equal to about 1.5. Okay, and so when I have this, I can plug this into the BJT current equation, and so I have the drain current is equal to I naught times e to the voltage difference. This would normally be VBE, but in this case it's VGS minus VT, divided by N, This is the prefactor that I have here, KT on Q. Okay? And so this should give me a sub-threshold slope of about 60 millivolts per decade below VT. Okay? And so this says that there is going to be current below VT, but it's governed by diffusion, which is how a BJT carries current rather than drift like a MOSFET. All right, so there's various different regions of operation. Shown here are a couple of them. If I have VT that's less than 0, we're going to call this sub-threshold. Once I have VT that is getting larger than 0, we're going to enter a region that's called moderate inversion. This is where we're starting to get inversion, but the channel is not really fully formed. And then we have this other region where VOV is greater than 150 millivolts. And that's what's called strong inversion. Okay? Our model that we derived is very good for strong inversion. Okay? This long channel model, it predicts very accurately what's happening in strong inversion. It did not do a very good job, / a good job at all, of subthreshold, and it only does an okay job in moderate inversion. And really, the reason why is very simple. We assumed the carrier mechanism was all based on drift, and so that puts us into this strong inversion where most of the current that's conducting between the drain and the source is driven by a drift mechanism. Down here in subthreshold, it's all diffusion. Okay, and so it makes sense that our model should not predict subthreshold properly. In moderate inversion, that is where we have a relatively low overdrive voltage, it's a combination of diffusion and drift. We did not account for the diffusion in our model, so it makes sense that our model would not accurately predict it. Okay? So what are we going to do in 164? Couple of things. One, we're going to restrict ourselves to operating in strong inversion. Okay? Why? Because I want us to be able to develop intuition and to be able to use the equations that we've derived to date and not try to worry about this behavior that we haven't really accounted for. Okay? We will not design any other circuits in this class that operate in subthresholds. Okay, so for all of our hand calculations, we will use back of the envelope assumption that ID is going to be equal to 0. In simulation, you will see that there is some current. It is almost always going to be negligible. When I say negligible, I mean it's going to be on the order of picoamps or nanoamps, and we're designing a circuit that is conducting tens, hundreds of microamps. And so it's a very, very small fraction. It should not have much impact on our behavior. And so, you may be saying, well, geez, why are we doing this? Like, why do we have these types of restrictions? And the answer is extremely simple. One, I want to develop intuition. I want us to be able to look at circuits, reason about their behavior without getting stuck in doing lots of math and solving equations until it comes to that point. We need to be able to distill down very, very complicated things into relatively simple concepts without getting bogged down in all of the other complexities that occur in these other regions of operation. Okay? You will learn about them in various classes later on in 203 and in 264 in particular. It's just that in 164, we're going to focus in moderate inversion so that we can use the model and we understand fundamental design trade-offs and considerations. Thank you.